Hello everyone, my name is Gong Wei. I came from School of Computer Science and Technology, University of Science and Technology of China. Today I would like to introduce our work in progress, widerframe, an automatic customization framework for building signal accelerators on FPGA. In recent years, with the continuous evolution of convolutional neural networks and the improvement of the computing capability of FPGA, the deployment of signal accelerator based on FPGA has become more and more popular in various computing scenarios. Different from the general purpose platforms, building an efficient signal accelerator on FPGA requires rich hardware development experience and a full understanding of architecture and application details. Therefore, in order to decrease the design complexity, the design of automatic deployment and optimization framework for FPGA-based signal accelerators has increasingly been a research hotspot in both the academic circle and industry community. From the nature of hardware acceleration, the primary aim of FPGA-based accelerator design is to fully exploit the customizability of FPGA to make the underlying hardware architecture and the up-level application features fully match. For this point, however, the existing frameworks have the following issues. First, there exist kinds of neural computing engines, and different engines have distinct paralleling characteristics for different signal models. Unfortunately, all the existing frameworks can only support one specific engine, and a lack of a cross trade-off. Second, the application mapping and the hardware implementation are tightly covered in the existing frameworks, resulting in a fixed execution pace for different layers. So it is hard to minimize the off-chip memory access by flexible data flow scheduling. Third, because of the coupling issue mentioned before, existing frameworks cannot provide flexible support for newly emerged convolution types. Even if the cooperators are invariant, there is insufficient backward compatibility for state-of-the-art signal models. To overcome these issues, in this work, we propose widerframe, a customization framework for building signal accelerators on FPGA. In addition to having an automated design process and programming interfaces compatible with the mainstream deep learning framework, compared with previous works, widerframe has the following features. Firstly, it covers three mainstream neural computing engines, including vector operator unit, two-dimensional systolic array, and window grid unit. Through a systematic and complete design space exploration, the real optimal accelerator architecture for implementing the target signal model on the specific FPGA platform can be obtained. Secondly, it adopts a layer-grained micro-instruction-based execution mechanism, and there is no coupling between the synthesis of hardware units and the generation of computation sequence. Therefore, it can have better compatibility to new convolution types through a handy instruction expansion. Thirdly, it contains a complete macro-instruction set related to different layer types with different data flow scheduling methods on various neural engines. Therefore, it can well support different data reuse methods for processing different layers. The overall architecture of a widerframe is shown in the figure, which consists of the user input, the design space exploration, and the accelerator generation, three parts. The framework receives the signal and FPGA descriptions and outputs the synthesizable hardware code and the corresponding micro-instruction sequence. White blocks in the figure represent the 7 main modules in the framework. After the programmer inputs the signal and FPGA descriptions, the info extractor extracts the hardware and the signal information from the user input. For subsequent DSE process, the hardware information includes the number of DSP and BRAM blocks and the theoretical off-chip memory bandwidth of the user FPGA platform. Then the engine filter receives info extractor's output information and conditionally filters out the unsuitable neural engines according to the nature of the CNN, so as to reduce the exploration space. After that, The DSE initializer abstracts and generates the paralleling variables and the constraint conditions of the DSE process for each candidate neural engines. And the excursion estimate will evaluate the excursion results of different neural engines with varying paralleling variables. When the design space explodes over, the optimal paralleling variables will be determined according to the related evaluation results by the recorder. The hardware code template uses determine the optimal paralleling variables to generate the synthesizable accelerator description. The template of 3 candidate neural engines are written in highlights-based C language to ensure the compatibility to different FPGA platforms. And the architecture parameters such as buffer size and the computing parallelism are well abstracted and can be initialized directly according to the optimal variables from the recorder. Correspondingly, the instruction library will generate the control flow related to the computation sequence of the CNN model. It includes layer-grained configurable macro instructions covering almost all known layer types in modern CNN models. For convolutional layers, different loop nested manners are organized at different instructions, and the loop iteration times will be determined jointly according to the explored architecture parameters and the layer structure parameters, and will be configured as operands in the instruction. To evaluate the effectiveness of the proposal, we implement ArcSnet VGG16, ResNet 50, and MobileNet version 1 on Xilinx Vortex 7 FPGA platform. According to the DSE results, ArcSnet and VGG16 are implemented with Vinogrid unit. ResNet 50 and MobileNet are implemented with 2-dimensional systolic array and vector operator unit, respectively. Compared with DN Builder, a representative automatic design framework before, widerframe on the one hand can support more efficient convolution types and CNN models, and on the other hand, for traditional CNN models, widerframe on average can achieve 1.25 times and 1.68 times improvement on the performance and energy efficiency respectively, with lower frequency and more moderate hardware resource requirements. If you have any question, welcome to contact and discuss with me. And that's all. Thank you.